Let me show you something strange. I'm going to use perfectly normal algebra to prove something impossible. I'm going to prove that 1 equals negative 1. Start with 1. 1 equals the square root of 1. And 1 can be written as negative 1 times negative 1. So we have 1 equals the square root of negative 1 times negative 1. Now here's the tempting step. Split the square root of negative 1, times square root of negative 1, and square root of negative 1 is I. So this becomes I times I. That equals negative 1. So 1 equals negative 1. That can't be right. Where is the mistake? To find the mistake, we have to look beyond the number line. We need a bridge between algebra and geometry. That bridge is Euler's identity. It tells us that e to the I theta is a rotation in the complex plane. Theta isn't just a number, it's an angle. Rotate all the way around, 2 pi. And you land back at 1. So 1 equals e to the I 2 pi. Rotate only halfway, pi, and you land at negative 1. So negative 1 equals e to the I pi. Same formula, different rotations. And this is where branches begin. Now let's ask a more careful question. Is the square root of e to the I 2 pi equal to e to the I pi? On the complex plane, e to the I 2 pi is a full rotation. You start at 1, go all the way around, and land right back at 1, so the input is just 1. But complex numbers come with a rule. We must choose a principal angle between minus pi and pi. For the number 1, that angle is 0. And the principal square root is defined using the logarithm. Square root of z is e to the 1/2 times log of z. So square root of 1 becomes e to the 1/2 times 0. That equals 1. Now here's the tempting thought. What about e to the I pi? That equals negative 1. But that value lives on a different branch. It is not the principal root. Now watch carefully because this is where the trap closes. First, with ordinary numbers, negative 1 times negative 1 is just 1. No problem there. And when we take the square root, the principal definition gives us the positive root. Everything behaves exactly as expected. Now we try the same idea using Euler's formula. Negative 1 can be written as e to the I pi. So we multiply e to the I pi by e to the I pi. On the complex plane, that's a rotation by pi, and then another rotation by pi. 2 half turns bring us back to 1. So again, the input is 1. But here's the catch. In the complex plane, numbers are not just values, they're reached by rotations. The final point looks the same, but the path we took is not. Now we finally take the step we've been holding back. What happens if we write square root of negative 1 times square root of negative 1? On the complex plane, negative 1 sits at an angle of pi. Taking the square root does not just change the number, it halves the angle. So square root of negative 1 rotates us halfway to I. That's the first root. Now we multiply by the second one. Multiplying by I adds another 90 degrees. That rotation takes us right back to negative 1. So the calculation says I times I equals negative 1. Nothing illegal happened. We followed the principal definition at every step. But notice what changed. We didn't just multiply numbers, we stacked rotations, and this is the moment where the shortcut quietly breaks. Now let's place the two calculations side by side. On the left we combine first. Negative 1 times negative 1 becomes 1. Using Euler's form, that's e to the I pi times e to the I pi. The exponents add, giving e to the I 2 pi. But on the principal branch, 2 pi wraps back to 0, so the square root becomes square root of e to the I 0, and the result is 1. Now look at the right side. Here we split the roots first. We take the square root of e to the I pi twice. Each square root halves the angle, so we get e to the I pi over 2 times e to the I pi over 2. Now the angles add. Pi over 2 plus pi over 2 equals pi. That gives e to the I pi, which is negative 1. Same symbols, same numbers, but a different order, and in the complex plane, order matters. Combine first and the angle resets. Split first and the angles accumulate. That's why these two expressions are not equal, not because math is broken, but because complex numbers remember how you got there. There is a rule that looks familiar. The square root of a times the square root of b equals the square root of a times b. That rule works perfectly when a and b are non-negative. But once we move into complex numbers, that rule breaks. In the complex world, square roots are multi-valued. They depend on angles and on the specific branch we choose. That is why the square root of -1 times the square root of -1 is not the same as the square root of -1 times -1. Thanks for watching.